a chapter that is going to cause you to think a lot. It's not as procedural, it's very abstract. And we're going to be dealing with concepts of infinity, which, tend to be a little bit philosophical. And I think I asked you all this question last couple weeks ago. Can you visualize adding an infinite collection of positive numbers and getting a finite result? That's a super important thing to be able to visualize. Adding a collection of positive numbers and getting a finite result. And can someone give me an example? Oliver?
Walking half the distance. You're going to a destination, you walk half the distance, and then you walk half that distance, and then you keep walking half that distance.
Wait, we don't want to know about Zeno's paradox.
Zeno's paradox?
We want to know, give me a numerical example of Hannah.
Adding a bunch of infinitely decreasing numbers that all add up to 1. They just keep getting smaller.
So 0.9 plus 0.09. Everyone follow that example? So this is, when you think about an infinite series, this is a fantastic example that you should have in your head. That this is an infinite collection of positive numbers, and we all know that this is going to be 0.9 repeating if you write it in that notation, or if you wrote it as an integer, that is actually equal to 1. And one thing that this illustrates is that the decimal representation of numbers is not unique. You can write 0.9 repeating or 1. Those are the same number. There is no space between them. Distinct numbers have space between them. So if somebody claims that 0.9 repeating and 1 are not the same number, you should be able to measure the distance between them. But of course you can't. If anyone says the distance between them is 100 zeros and a 1, you just go a little bit further out and you can prove that that's not true. So you can prove by contradiction that there is no space between those two numbers which make them the same. So decimal representation of numbers are not unique. These are all positive. And one necessary condition to have an infinite collection of numbers that add up to a finite result, one necessary condition is that the numbers have to be going to 0. If the numbers aren't going to 0, there's no way the whole sum could be finite, because it's like blowing up a balloon. Eventually it's going to explode, right? You need to be adding microscopic amounts out in the tail, or that sum cannot be finite. Okay, so it's necessary that these terms go to 0, but it is not sufficient. So you're going to hear those words as you go on in math, necessary and sufficient. And here is an example of a series called the harmonic series, probably the most important series that we'll look at, because it's a reference series that we see all the time. Those terms are going to 0, but that sum will be infinite because those terms aren't going to 0 fast enough. So that series is going to diverge or have an infinite value. It's not going to be finite. It's not going to converge. So those are two fantastic examples to have in your head anytime you're thinking about a series. Because what we need to be doing, which should remind you of the improper integration that we just did, some functions go to the x-axis fast enough that we got finite area. Some functions went to the x-axis but not fast enough, and we had infinite area. 1 over x did not go fast enough, so it had infinite area. But 1 over x squared, 1 over x cubed, 1 over e to the x, all those things went to the x-axis fast enough that the area underneath was finite. So those are the ideas that we want to be thinking about. And we're going to spend a lot of time in this no man's land right in between trying to figure out, okay, the terms are going to 0, but are they going to 0 fast enough? That's going to be the ultimate question. Are the terms going to 0 fast enough that we can get this finite result here? That the result is not infinite. So that's what, when you look in OneNote and you go to the handouts and you look at all this stuff here, like these convergence tests, that's what these are all about. There are very few series that we can actually analyze directly. Like there's very few that are going to have a formula that will tell us what to do, tell us whether it's finite or infinite. Most of the time, we're going to be dealing with this stuff where we can prove that it converges or prove that it diverges, but we won't have a clue what it converges or diverges to. So we have this sort of end around way to figure out, do we have convergence or divergence? So a lot of times we can't analyze directly. We've got to use one of these more general tests. And again, it will tell us perhaps that we have convergence, not the divergence test, that doesn't tell convergence, but this integral test. It might tell convergence, but we won't necessarily know what it converges to. There's very few series that we can actually find the sum of. It's a very difficult task to add an infinite collection of numbers and know what the result is. Like that's a big deal, being able to add up an infinite number of numbers and know what the result is. So the concepts are, abstract, but they're super important. And you may say to yourself, well, why are they important? We never add up an infinite collection of numbers. Where are we going to use these series? And every single one of you that has a phone or a calculator, a computer, that's where you're using infinite series all the time. Do you think, when you type into your calculator sine of pi over 3, what do you think the calculator's doing? The calculator has an infinite series built in for sine, and it goes far enough out. I think it's pretty intuitive that the further out you go, the closer you get to the sum, right? If you want to be within 0.000001 of the true answer, you have to go far enough out to get within that threshold. So the further you go out in the series, the more accurate you're going to have as your approximation. Your approximation will be more accurate. And that's what a calculator or a computing device does. It has this infinite series with a remainder thing built in, and it just goes out far enough so that the numbers you see are accurate enough. If your screen holds 15 places, it needs to be accurate within 16 places or whatever. So all of the computing devices you use have this stuff built into the background. So that's super important because they are used, perhaps not in the forefront, but they are behind the scenes all the time, these infinite series. So 10.1, there are two things. There are two things we're going to look at, and 10.1 kind of gives us an overview of both. There is something called a sequence and something called a series. A sequence is just a list of numbers. It's just a list of numbers. And the sequence could converge or diverge. And then a series is a sum of a sequence of numbers. And then in the next chapter, we'll talk about an infinite sum of functions. Not just an infinite sequence or a sum of numbers, but we can have an infinite sequence or sum of functions, which makes it even more complicated. As soon as you put a variable in anything, things get a little more complicated. So let's distinguish. This section is going to just give us an overview of sequences and series, and then we'll dive into details and sequences for 10.2, and then the rest of the chapter will be about series. But you can't understand a series unless you understand a sequence first, so that's where we're going to start. So a sequence is just an ordered list of numbers. And you can generate your ordered list of numbers typically in two ways. We often will use an explicit formula, and an explicit formula builds the values in your ordered list by looking at the index value and doing something to it. So the index value will be the input. And you've got a function that takes that index value and builds a number. So that's the most common way that we are going to see, where we build our list of numbers with a function. That's going to be the most common way. The other way, which you will see from time to time, is this method using a recurrence relation. So using a recurrence relation, you are going to generate the next term from the prior term. So instead of looking down at the index and saying, hey, take the index and square it, or take the index and cube it, or whatever, instead you look at the prior term and you do something to the prior term to get to the subsequent or next term. Does anyone know a recurrence relation or sequence? Super common one, a super popular one. I'm sure you've all heard of it. The one I'm thinking of depends on the prior two positions to create the current position. Even numbers are a sequence, for sure. Those we would add 2, so that's a recurrence relation. We do repeated adding of 2. But there's a really famous one, begins with an F. Fibonacci. Fibonacci is the most probably well-known sequence that's given by a recurrence relation. You take 2 terms and you add them up, and that's what gives you the next term. So it starts with 1 and 1, and the next term is 2, and then you add the 1 and the 2, and you get to the 3, then you add the 2 and the 3, and you get to the 5, then you add the 3 and the 5, and you get to the 8. So Fibonacci is probably the most well-known sequence that's given with a recurrence relation. But we're not going to look at that too deeply. We like functions because with functions you can do things with functions more easily. This kind of looking at the prior term to get to the next term, that's not as easy to analyze as it is to analyze something that's given with a function. So there are lots of notations for sequences. We usually use the curly brackets or braces to house a sequence of numbers, and the terms are separated by commas. Whereas if you look over here at a series, the terms are separated by addition. So that's the big difference. Moving from a sequence to a series, we turn the commas into addition. A series is adding, a sequence is a list. We'll see it like this sometimes, but we'll see it like that most commonly. It's going to be seen like this. Once you get into calculus, if a sequence is not infinite, they're going to make really clear that it's a finite sequence. They're going to say it's a finite sequence. From here on out, if you hear the word sequence or series, you should be thinking infinite. If it's not infinite, they will tell us. Right? They'll have to make it clear that we're looking at a finite sequence where n goes from 1 to 10, or from 5 to 100, or whatever it is. Typically, we will start our indexing with 1 or 0. We will see that sometimes it's, because of the nature of the sequence or the series, it might be better to index starting at 0 instead of 1. But it's very rare that we would start with something other than 0 or 1. When we think of this explicit formula, a sub n equals f of n, so in other words, the nth term is a function of the nth index, that tells us that a sequence is really a function. But it's a discontinuous function. When you're visualizing a function, when you're visualizing a function, a sequence that is a function, what you're visualizing is that your domain is this discrete set of integers. So there is a picture of a sequence, and we can imagine it going on forever. So the domain is the set of usually natural numbers, or the set of positive integers. It just depends. And it's discontinuous, right? It's a discrete function. A sequence is a discrete function. Everyone follow that? So discrete means just this set of points. Right? They're not connected, so it's discrete or discontinuous. So when you hear sequence, that's another great visualization. You're imagining this discrete set of points. And we usually are going to draw them this way, because if the terms aren't even going to 0, we know that there's divergence if we were dealing with a sum. You could have a sequence that converges not to 0. That's certainly a possibility also. We will be looking at this a lot less than the other scenario, because we are really going to gear ourselves up for series, which means that the sequence of terms has to go to 0. But you could have a sequence that converges like that to a horizontal asymptote. Very possible. But for us, most of the time, when we are visualizing sequences, this is the way you should visualize them. They're going to 0, and you're questioning whether they go to 0 fast or slow. OK, so the domain for a sequence, again, set of non-negative integers, set of positive integers, the natural numbers, whatever the case may be. But it's discrete. So for example, we have this sequence, 1 over n. Again, that is the harmonic. That over there, I've written it as the harmonic series. Here, I've got it as the harmonic sequence. So the harmonic sequence is right here. And you can visualize that those terms are going to 0. Right? So the limit of the harmonic sequence is 0. The harmonic sequence converges to 0 because these values are going to 0. But the harmonic series diverges. So the harmonic series is the sum of the terms in the harmonic sequence. So the harmonic sequence converges to 0, but the harmonic series diverges. So if we were to add all these heights up, that is not going to be a finite result. That will be infinite. So when you're thinking about a series, you should be thinking about areas, right? There's a rectangle that has area 1. There's a rectangle that has area 1/2, right? If the width here is always 1, then the height here is actually the area of that rectangle. If the width is 1 and the height is 1/2, the area is 1/2. So we have that you can always visualize a series as a sum of rectangles. Okay, so these areas are also the heights. Right? Those are the same. The height and the area are the same here because the widths are all 1. OK, so that sequence converges to 0. Limit of a sequence, just back to Calc 1. So we say that the limit of a sequence is a number L if the sequence gets arbitrarily close to that L value. Usually we're thinking about L as a y value, like this y value of 0. Like that is a very good way to visualize. Right here, we would call this the L value. You know, if it's going to converge, right, these sequence terms are getting arbitrarily close to L. And so that is our formal definition. So the limit of a sequence will be L if the sequence converges. And we say the sequence converges to L. So it just means that as n increases, we're getting tighter and tighter and tighter. We're getting arbitrarily close. If someone wants to say, get within 0.1, you can say, oh, if I go out to the 1,000th term and beyond, then we'll be within 0.1. So arbitrarily close, it's kind of like a ratchet, just getting closer and closer and closer as you go further and further out in the sequence. So it's like a ratchet. It's ratcheting tighter and tighter. So that's the notation. Limit of the harmonic sequence is 0. So we have our two basic limits that we're going to look at a lot. 1 over n goes to 0 as n goes to infinity. And n, the limit of n as n goes to infinity, is infinite. Those are our two basic limits. The limit of n as n goes to infinity is infinity. Limit of 1 over n as n goes to infinity is 0. So we can usually break things down to one of those two basic limits. we can also have sequences that have negative values. So we could have this sequence right here. This is called the alternating harmonic series. So we can take the alternating harmonic sequence and then add all the terms together. That would be the alternating harmonic series. The alternating harmonic sequence right here, there's 1, negative a half, plus a third, minus a fourth. And a lot of times I'll just include the Desmos instructions if you are playing around with Desmos and you want to learn how to do sequences and series in Desmos. I'll put some instructions there just so you can see how to do it. So for example, here I built the function 1 over x as the dashed curve. And to do a sequence, you just use a comma. It's just an ordered pair. And comma, and then I have this negative 1 to the n plus 1. That's just going to alternate the signs. And that negative 1 to the n plus 1, usually we call that the switch. So we can have a negative 1 to the n or a negative 1 to the n plus 1. That'll switch. That just toggles it back and forth between positive and negative values. So there is a picture of the alternating harmonic sequence. The alternating harmonic sum, or the alternating harmonic series, will converge. This will converge. This is going to converge to the natural log of 2, which is not easy to show, but it does converge to the natural log of 2. So if you think about that, what that means is that here we have there's our rectangle of area plus 1. Well, right here we have, if we want to think in terms of area, that value right there, the area is 1/2, but we're subtracting it off. And so there's this little tug of war going on where we're adding and subtracting repeatedly. So here we're going to subtract a fourth and then add a fifth. And this series, if we add all those rectangles together, if we find the net area, or we call it the signed area actually, the signed area, where you take the upper areas and subtract off the lower areas, that will be finite. So the harmonic series diverges, but the alternating harmonic series will converge. So you're subtracting off enough that if you look at these in blocks of 2, you can think of that as a block, so that's going to be a 1/2. You can think of that as a block, and that's going to be 1/3 minus a fourth, whatever it is. That new analysis will create something that does converge. All right. Working with sequences. We are not going to, the stuff that we're going to do on this slide is stuff that is just going to help us think about sequences. We're not going to do a lot of this in the long run. Trying to find a formula or a pattern is very, very difficult. So we're going to do a few of them so that you get a taste for it, but we're not going to spend a lot of time on this, but it's a very good mental exercise to see if you can do it. So the first thing here says find the next 2 terms in the sequence. That, of course, is not too difficult usually. Usually you can see the pattern. It's putting math to the pattern that's the hard part. Like here we can see that, okay, we're adding 3. So if we have 11, the next term, so we're going up, let's just suppose we're up to 11 now. The next term is going to be 14, 17, 20, etc. Yeah. So we see that that's what the pattern is. We're doing repeated. So this is recurrence. The natural way to think about this is recurrence. You're taking the prior term and you're adding 3 to get to the next term. Okay, so B says, find a recurrence relation that generates the sequence to apply the initial value. So what we are going to do is this. We're going to say that a sub n plus 1 is a sub n plus 3. So we get to the next term by adding 3 to the current term. Simple enough. But we also need to know where we're starting. What are we adding 3 to in the first case? Right? We need to know where we're starting. We can't just say add 3 repeatedly to the current term if you don't know what the current starting term is. So we need to indicate a starting term. So a sub 1 in this case is going to be 2. That's our starting term. So if we define a recurrence relation, we need to say where we start. So a sub 1 is going to be 2, and then to get to a sub 2, we're going to add 3 to a sub 1, and then we're going to add 3 to a sub 2, and then 3 to a sub 4, etc. So you need to know where you're starting. You need to know the little jump, but you also need to know where to start. Now the harder one, sometimes one is easier than the other. So we're trying to deal with a recurrence relation. That was very easy here. If one is easy, usually the other one's a little harder. So let's try to come up with an explicit formula. So what I find very helpful is to put the term number below it. Putting the term number below is super helpful just in terms if you're trying to find a functional representation. So if you put the term number below, our goal is to look at that n value, the index value, and create the term. And it's certainly not obvious. Usually it's not obvious. Can anyone see it? So most often, if it's not jumping out at you, we need to be a little bit more strategic. So here's what I'm going to suggest. Let's say, okay, well, let's create a little table. Usually, if we are being asked to figure out an explicit formula based on the index, there's some general relationships that tend to happen. So let's take a look at a table here, and let's just, like if I was doing this at home, one of my sons was in a computer science class. We just went to Excel. He was asked to find the pattern. It's like, okay, well, it's not obvious. Let's just do a bunch of stuff. Let's create a bunch of tables and see if we can figure out the pattern by just doing this kind of thing. Let's just assume it can't be that complex. So let's look at n, 2n, 3n, maybe n squared, things like that. Looking at common patterns. And let's see if we can figure out what's happening. So they tend not to be obvious, but if you do a little bit of, kind of looking around, and there's no way to just say this will work all the time, you have to just sort of try to be creative. And does anyone see what the function would be? So here is our index value right here. These are the indices. So we're trying to get to these values from here.
3n minus 1.
3n minus 1. That is the functional relationship between the term and the index. That's exactly it. So a sub n is going to be 3n minus 1. Let's look. So if we look at this 3n column, and then we compare it to our terms, oh yeah, 3 minus 1, 6 minus 1, 9 minus 1, 12 minus 1, that is going to be the functional relationship. That is going to be how we can write a term as a function of the index. So we're going to figure out the term's value by looking at the index and doing something, creating a function of the index. Perfect. But again, it's a pretty simple relation to come up with the recurrence relation. Pretty simple, but that's a lot harder. You have to have some strategy. To come up with that out of your head without sort of looking at some more broad patterns is hard. So that's my recommendation. And if this didn't work, I would say, oh, well then let's look at n squared perhaps. Just look at different things that are not too complicated. Because if they're asking us to do something, it can't be, it can't be like sine of 2 pi n divided by n squared plus, they're not going to give us something crazy. We don't want something crazy. We're trying to figure out some function patterns that are not too complicated. Okay, so another one here. Pretty obvious that we are doing repeated division by 2. So if we're down here at the 4, we're going to do repeated division by 2. So this is where we would be going if we continued on in this sequence. Repeated division by 2. And once again, we see that the recurrence relation here is pretty easy. The recurrence relation just says you get to the next term by taking the prior term and dividing by 2, and we are going to start at 64. So a sub 1 is 64. To get to a sub 2, you have to plug 64 in right there, divide it by 2, then you plug 32 in right there. So you do that repeated division by 2. So in this one, again, the recurrence relation is easier, which probably means the other one's more difficult. Quite frequently, if one is easy, the other is harder. And once again, my recommendation is put your index values right down here, and that usually will help. And if the pattern's not leaping out at you, create a table. Come over here, create a table. Let's look at some things in our table. So we have our index value, and what do you notice? What's one thing you notice about all those numbers? Say that again? They're definitely even. We can be even a little bit more precise. Not only are they even, they are also, like 6 is even, but it's not going to fit into this pattern. What kind of evens are these? They're all powers of 2. They're all powers of 2, right? They all have a power of 2 in them. So let's say, okay, well, what do powers of 2 look like? So if we're seeing all these powers of 2 right here, right, those are all powers of 2. It's getting us a little bit closer. We start to see, oh, it's kind of those things backwards, isn't it? Right? So, all right. What do you think? You see it yet? Let me go one more. So if I go 7, well, at least think about 7 right there for a second. Anyone see it yet? So what is the, let's put the powers up here. So the power for 64 is 6, right? That's 2 to the 6. This is 2 to the 5. This is 2 to the 4. This is 2 to the 3. This is 2 to the 2. What do you notice about the sum of the power and the index? So if we add these two, what are we getting in all cases? We're getting 7 in all cases. So what if we did something like 2 to the 7 minus n? So if we do 2 to the 7 minus n, when n is 1, we get 2 to the 6. When n is 2, we get 2 to the 5. When n is 3, we get 2 to the 4. And so not obvious. Definitely not obvious. But you can imagine if you create some general strategic infrastructure behind it that you can eventually get to it if you play around with it enough. This would be a miserable thing to try to figure out on an exam. When you're in a timed situation, this is not something you want to be doing. So I will not put these on the exam. Trying to find a pattern and mathematize it, is that a word? That would be very difficult. So we will not put these types of things on exams, but there will be some in the homework. Okay, here's another one. So A, so let's see. What do you think the next term in this sequence is? Yeah, so here the recurrence, the explicit formula is a little bit easier than the recurrence relation. This one's going to be backwards. Because I think you're all seeing part C right away. What's a sub n equal to?
N squared.
N squared, yeah. So if we put our little n values down here, this particular sequence, the explicit formula or the functional formula is pretty easy. So now the recurrence relation is going to be harder in this case. So and that's pretty common, that one is easier than the other. Okay, so let's see. Any ideas? So we have to say, how do we get to the next term from the prior? What are we going to do to the a sub n? So we're trying to get 4 from 1. We're trying to get to 9 from 4. I'm going to draw a suggestive path. How do we get to 9 from 4? Say that again? That's true, but that pattern's not going to then hold for 9 to 16. How do we get how do we get to, if we know isn't the index value the key?
Yeah.
Index value is the key. So if we're at 4, how do we get to its index value? Square root. If we're at 9, how do we get to its index value? If we're at 25, how do we get to its index value? Square root. So if the index value is the key, right, the index value of subsequent terms, we just increase by 1. So if we take 4 and we get to its index value, and then add 1, then we can get back up to the term value. So what we're going to do is say, take the square root of a sub n. The square root of a sub n drops us down. Then we're going to add 1, and then square it. Whoa. Wow. So that'll be the recurrence relation. So we're square rooting the term value to get to the index, and we're bumping the index by 1, and then we're squaring back up again. And double check, so if we're at 36, square root of 36 is 6, add 1 to it, that's 7, and then square it and we get to the 49. So these patterns are not obvious. Usually one is easier than the other, but important thought exercises for sure. Okay, page 5. Limits of sequences. All right, when you look at that sequence right there, 10 to the n minus 1, what's the limit of that? Infinity. As n grows without bound, and usually with sequences we're thinking of integer values. So we're thinking 10 to the 1 is 10, subtracting 1 is not going to do anything if you go far enough out with the n values, right? Subtracting 1 is insignificant. 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5, 10 to the 6, 10 to the 7. That's going to infinity, right? If you have a base that's larger than 1, and you let the exponent go to infinity, that's going to go to infinity. That limit will be infinity. Right? 2 to the n goes to infinity. What if the base was less than 1? What if we had 0.5 to the infinity? Go to 0. Right? That's one of our basic mathematical facts, that if you take a number bigger than 1 and multiply itself, it grows. 2 times itself grows to 4. 5 times itself grows to 25. But if you take a fraction, a true fraction, a proper fraction, 1/2 and you multiply it by itself, it shrinks. 1/2 times 1/2 is a 4th. Right? So we have that thing that we have to be aware of. Right? If we're above 1, whoop, goes off to infinity. Below 1, whoop, goes down to 0. So that's going to be important to have have right in the close at hand. So this is going to be infinity. So we're going to say the limit as n goes to infinity of 10 to the n minus 1. This is going to be infinity. So this is one of our basic limits again. a number greater than 1. If the exponent's going to infinity, the result will be infinite. Now let's look at this one. So here, we're going to have the limit as n goes to infinity of 1 minus, and when you're dealing with limits, especially limits at infinity, it's almost always easier to see if you have no negative exponents. Obviously, it's not necessary, but usually it's a little easier to see. It's like, oh yeah, that 1 over 10 to the n, that's going to 0, right? It's a little more obvious there. Now, if you're great with exponential decay functions, you might just see it right here that, oh yeah, of course, that's an exponential decay going to 0. But if it's not totally obvious, get rid of your negative exponents because it will be more obvious without negative exponents. So in this denominator, we have a 10 to the n, so that denominator is growing without bound, which means the fractions are shrinking to 0. If the denominator grows, the fractions shrink. 1 over 10, 1 over 100, 1 over 1,000, 1 over 10,000. Right? Fractions are shrinking to 0. So we say that the limit is 0 of that term, and then the overall limit will be 1. And this is just a picture of it in Desmos. So this sequence right here, you can see it's got a horizontal asymptote of 1. So if somebody said, create the series associated with this sequence, do you think we'd have convergence or divergence? Divergence. Because these terms are approaching 1. What would happen, let's just suppose we assume that all those terms are 1. What is true about this series? What do you think that series will do? Infinity. If you add 1 to itself an infinite number of times, that is not finite. So once again, a necessary condition for convergence of a series, a necessary condition is that the terms have to be going to 0. If you're adding an infinite collection of terms, and those terms aren't going to 0, that infinite collection is going to be growing without bound. So if we start adding all these terms together that are not going to 0, we're going to have something more like this that's going to be infinite. So we have to have the quarter pipe looking thing. We have to have that if we are going to have any chance for convergence of a series. Okay, so any questions on two basic limits here? Base greater than 1 in the numerator, base greater than 1 in the denominator. All right, so we've got to keep those two things in mind because, oh, let's look at this first. Okay, so here we have a recurrence relation. So this is a sequence that's generated recursively, and they tell us what the first term is. They have to tell us the first term. If they don't tell us the first term, we don't know what we're recursifying on. So we plug in the 1, and here I just did it in Desmos. Functional notation works great in Desmos, so I created the function, 10 over x. I said, okay, I'm going to start with 1. I did functional notation, a of a sub 1. Plugging in a 1 right there, 10 divided by 1 is 10. Now we plug the 10 back in, so a sub 3 is going to be that same function, but we're going to put a 10 inside, so a of 10 means 10 divided by 10, which is 1. Then we put a 1 back in, and we're back to 10. Then we put a 10 back in, and we're back to 1. Then we put a 1 back in, and we're back to 10. And you can see that this, if we were to write out the terms of this sequence, we start at 1, bump to 10, back to 1, back to 10, etc. There's a picture of our sequence. Does the limit of a sub n exist? No, because remember that for a limit to exist, the terms in the sequence have to get arbitrarily close to a single value. That's what limit means, right? The limit of a sequence is a number if the terms in the sequence get arbitrarily close to that single L value is what we usually call it. And these are not getting closer to a single number. So we say D and E. That does not exist. Now, let's go back to the prior slide for one moment. This limit right here that we said was infinity here. I just want to be clear that this limit does not exist. Even though every textbook and every teacher will say the limit is infinity, it makes it feel like we're saying the limit exists and is equal to infinity. This is horrible notation. This says the limit is infinity, but that doesn't mean the limit equals infinity. This limit, it's correct to say that this limit does not exist. This limit does not exist, but when we write infinity, we're giving a little extra nuance to how it doesn't exist. Right? We are saying it doesn't exist in the sense that it's going off to infinity. Whereas we cannot do that with this one. With this one, it's not going off towards infinity or negative infinity. All we can say is D and E. We can't add that extra nuance because it doesn't exist there. So it's very similar to this scenario when we're back in Calc 1, when you were dealing with vertical asymptotes. So let's suppose we have something like this. This function right here, if we call this C, all you can say here is if somebody says, what is the limit as x approaches C? Not one-sided. If they write that, that means two-sided. All you can say is that this limit does not exist. Right? You cannot be more precise with that two-sided limit. Whereas if the function had this type of asymptote situation, that does not seem to take away the little, oh, that did work. Okay. So if you had this scenario here, we'll use green again. If we had that, and that's C, here you can be more nuanced. Here you can say the limit of f of x as x goes to C, that is infinity. We say is infinity, but what we mean is that regardless of whether you come into C from the right, left, or you come into C from the right, doesn't matter. The values of the function are going towards infinity. They're growing without bound. Now here, you could be more nuanced about the one-sided limits. Here you could say the limit of f of x as x approaches C from the left is infinity. And the limit of f of x as x approaches C from the right is negative infinity. So you could be more nuanced there, but with the two-sided limit, you cannot be. You have to be very general. The limit doesn't exist. You can't indicate how it doesn't exist. So keep that in mind. It can be a confusing thing. So here, all we can say is that the sequence is not getting arbitrarily close to a single number, therefore the limit does not exist. That's what we say. OK. This one. So here again, recursive, did the same thing in Desmos, just to plug in the values, just to show that you could do it in Desmos easily. If you plug in a 2, you get 1 plus 1, which is 2. Oh, plug in a 2, you get 1 plus 1, which is 2. Oh, plug in a 2, you get 1 plus 1, which is 2. And we see that this sequence is very boring. That sequence, if we were to write out the sequence, is just that. Does this sequence have a limit? So what would we say? 2. Okay. We're getting each, as we go further and further out in the sequence, we are arbitrarily close to 2. In fact, we're as close to 2 as you can get. We are 2. So that sequence has a limit. The limit of a constant is itself. The limit of a constant is itself.
Wait, for this one, why did you start at a of 0 instead of a of 1?
That's just, so they have to tell us what the first value is, and they're just telling us that we're going to count from 0 instead of 1.
Okay. so it
Totally.
doesn't- It has, but it has to be 1 or 0, right?
It has to be the first term in the sequence. If they wanted to be, contrarian, they could say, hey, we're going to start at a sub 5.
Okay, and then that would work too.
Yeah, so what we normally do is start at 0 or 1.
Okay.
And it kind of depends. We'll see that there are some series that are easier to describe if you start at 0, and some series are easier to describe if you start at 1. There are some times where if you start at 0, you get division by 0, so they don't want to start at 0, they'll start at 1. It just kind of depends on the nature of the sequence of series. But 99% of the time, we're going to start at 0 or 1. You could start other places if you wanted to be contrarian, though. Okay, so 10.1 again is just a brief overview of sequences and a brief overview of series. So this is sort of like a heads up, this is where we're going type of thing. So let's do this brief overview of series. We're starting with the sequence of numbers. A sub I, A sub n, whatever you want to think of them as. We have a sequence of numbers, and then we're going to add them together. That is what we're going to call a series. And when we use the word series in this class, we mean infinite series unless they tell us it's finite. So we have this infinite series. This is the notation. You've all seen that. Greek letter sigma, Greek letter for S for sum. So that is the series notation to add up these A sub n's, A sub i's, A sub k's, whatever they happen to use. All right, so we are going to have 3 things going on. We are going to have our sequence of terms. That's the A's, sequence of terms. We are going to have the series, which is the sum of terms. And we are going to have a secondary sequence called the sequence of partial sums. So we start with our sequence of terms. We're trying to analyze what happens when we add them all together. The way that we analyze a series is to create a new sequence. One sequence and one series is not enough, so we create a new one. And this is called the sequence of partial sums. So that is the new series. That is the series that we want to analyze to figure out whether the original series converges or diverges. So all we're doing is creating partial sums. We're just going one term further out. So we're doing this kind of thing. So here would be S sub 1. And if we add one more term, there's S sub 2. And if we add one more term, there's S sub 3. And if we add one more term, there's S sub 4. So the sequence of partial sums is creeping out into the series. It's taking one term at a time. So it is building a sequence that's going to get closer and closer slowly to the sum of the series if the sum of the series exists. Right? So as we go further and further out, one term at a time, if the series converges, that sequence of partial sums is getting closer and closer. So we are creating a sequence that will have limit equal to the sum of the series. So S sub n is the sum of the first n terms. That's what S sub n will mean. Sum of the first n terms. If we had a series that started with its index at 0, what do you think the index of the nth term would be? So if we start at 1, the nth term obviously will have an index of n. The 5th term has a 5 as the index. The 6th term a 6. Nth term an n. If you started counting at 0 instead of 1, what would the nth term's index be? N minus 1. Right? So we have a little shift. If we're starting at 1 and going to n, and then we start at 0, then we're going to go to n minus 1. There's going to be a shift to the left of 1 with all the indices, just as a heads up. Okay, so the sum of the first n terms, this is a finite sum right there. You see the n in the top position up there. That tells us that we're stopping, that this is a finite sum. This is going to have n terms added together. So that's a finite sum. And so it always is going to be super clear when we're dealing with finite sums because they tell us that we're stopping. We're only going to let the index run from 1 to n. Okay? So here's what we're going to do. This should remind you of an improper integral. What did we do with an improper integral? We created a definite integral, but that definite integral was a function. Maybe we used a b or an a or a c, but we ended up getting a function, and then we took the limit of the function. Same idea. We are going to create our partial sum. So our partial sum is analogous to that definite integral where we integrated from, say, 1 to b, and then we took the limit as b went to infinity. Same idea. We're going to get our partial sum here. There's our partial sum, and then we're going to take the limit. So we build our partial sum, and then we take the limit. The partial sum is called S sub n, and that'll be the limit of the series, if it exists. Now that looks pretty darn simple. It's like, oh wait, all we do is create S sub n and then take its limit? That doesn't, like, why is it 2 chapters? If all we have to do is find S sub n and take the limit. Well, it's 2 chapters because finding S sub n is extraordinarily difficult, if not impossible. We are going to see that this is more of a conceptual understanding. We are going to see that there are only 2 types of series that we can actually find S sub n for. Those are going to be geometric and telescoping. Those are going to be the only 2 series that we can actually find S sub n. Those series are going to be pretty darn easy to analyze because we can find S sub n and then just take the limit. We know how to take limits. Right? With our basic limits, we can use that to take basically a limit of anything. So geometric and telescoping are going to be the only ones that we are going to see that we can actually get to that S sub n easily. Most series you cannot find S sub n. And that's what that page of all those tests are. Because you can't find S sub n, so you have to analyze with another way. All right, let's take a 10-minute break, and then we will carry on. Fact. Oh, yes, Federico wants to say something. Okay, so one of the simple examples that I kind of illustrated already with these infinite series is that repeating decimals are good examples of infinite series in disguise. You know, you don't really think of it, but 0.9 repeating or whatever number we choose is really an infinite sum, right? You're thinking about adding repeated addition all the way through. And so 1/9 is 0.1 repeating. So this infinite series right here converges to 1/9. So this is the sequence of terms. And then the sequence of partial sums. So this is a very, it sounds easy. Sequence of partial sums, you just keep adding one more term. Like, it sounds easy, but it's very easy to get tangled up. And so one thing I would recommend is always asking yourself, am I dealing with the sequence of terms, or am I dealing with the sequence of partial sums? Like, it's really important to distinguish the two. So notice that the sequence of terms, these are the things that are getting tighter and tighter to 0. If those aren't going to 0, you know that your series will diverge. Again, because if you start adding 1 plus 1 plus 1 plus 1, you get infinity. So if any positive number, if you added 0.1 plus 0.1 plus 0.1 plus 0.1, that would also go to infinity. You have to be adding terms that are shrinking to 0. So if you're not shrinking to 0, you definitely don't have convergence. So there are the sequence of terms that are shrinking to 0. And then here is the sequence of partial sums that are getting incrementally closer to the sum of the series. Everyone catch the difference? So if we look at pictures, if we were to draw the sequence of partial sums, we keep adding, so the y values are the sequence values right here. So 0.1 is the y value, 0.11, 0.111, etc. So you can see that these y values are getting closer and closer to whatever this number is here, to the limit of the sequence, to the limit of the series, or the value of the series. The limit of the sequence of partial sums is the sum of the series. Now, if you were to graph these terms here, those would all be going to 0, right? Those are down here. Excuse me. Is it going to happen? False start. All right, so there are the sequence of terms down there, and these are the sequence of partial sums up there. So the sequence of terms has to be going to 0, and then the sequence of terms for the partial sums will be approaching whatever the limit of the series is, or the value of the series. Okay, so this is kind of a good example. We know that the sum of that series is going to be 1/9. Let me bring you back to a topic that we used to cover in algebra that seems to be no longer covered in algebra, at least unless I have a bunch of lying students. I never saw that before. The number on the right, 1/9, that is a rational number because it's written as a ratio. Right? Rational number is written as a ratio. And we have been told our whole lives that repeating decimals are rational numbers. Everyone agree with that? If your number doesn't repeat and goes on forever, like pi, then it's irrational. Irrational is the decimal expansion goes on forever with no pattern. Rational numbers have a pattern. They have a repeating decimal if it's rational. So if that's the case, okay, then this number right here is a rational number. Everyone agree? That is rational. If it's a rational number, it can be written as a ratio. How do you write that as a ratio? Does anyone know the Algebra 1 steps to write that as a ratio?
Is that technique where you would do something to
Yes!
and then
You do something.
subtract it from itself to. I remember seeing where you have the repeating and then you do something. You take the same repeating and you do something to it and then you subtract it from it and it gives.
I think what you're thinking of is the geometric series proof, because the geometric
Maybe.
series proof is like that, where
Okay.
you sort of shift it and subtract it from itself.
Yeah.
That
And it-
this is a little. What letter do you think of when you hear the word algebra? Okay, let's do that. Let's multiply both sides by something like 100 in this case. And I'm multiplying by 100 exactly so that I can create an integer in front. That is a period. An integer in front. Do you agree that this is really, a decimal point is really a hidden addition? Right, we could do that.
Oh yeah, then if you subtract x from that, you get 99x.
So
You get-
0.25 repeating is right
Yeah,
there. That is
yeah.
x.
And then you get rid of the repeating, and now you have the.
So we've now gotten rid of the repeating part of it.
Yes, I
And so now we just subtract x and divide by 99. So we'll have 99x equals 25. So x will be 25/99s. So that's that's the algebra method to go from the repeating decimal to its rational fraction form. All right. So, yeah, I feel like they don't do that in algebra anymore.
I remember learning it.
But you didn't go to school.
I went to college algebra.
Oh, you
And-
did?
Yeah, I came here to do college algebra, and then I used that to
Pre-calc. But you didn't do this in college algebra, did you?
No, I did.
You did?
I
Here?
did. Yeah.
Oh,
I did that here.
interesting.
I remember. When am I ever gonna need this?
Okay, well, welcome. Welcome to the future.
Here, I hope you'll teach me a better way to do that same thing.
Okay, so this says for the following infinite series, find the first 4 terms of the sequence of partial sums. So here is our sequence of partial sums. So it says find, we're going to just write S sub n in this way. So it said put at least the first 4 terms in. So here is our sequence of partial sums. That is our sequence of partial sums. So S sub 1 is just the first term in the series. So there's S sub 1. S sub 2 is the sum of the first 2. S sub 3 is the sum of the first 3. S sub 4 is the sum of the first 4. No, because we're adding. Right? S sub 2 is that plus that, which is this. So we add, so S sub 2 is the sum of the first 2 terms. So S for sum, sequence of partial sums. So we're adding the first 2 terms to get to here. We're adding the first 3 terms to get to there. We're adding the first 4 terms to get to there. So the sequence that you're referring to is the sequence of terms. And the sequence of terms will have the zeros. So here is the sequence of terms. So there's the sequence of terms. Sequence of terms, sequence of partial sums. Then make a conjecture about the value of the series. So let's take the limit of S sub n as n goes to infinity. And that limit is going to be 2/3. That is the limit of this sequence of partial sums. 0.6 repeating, which is 2/3. Yes, indeed. All right, so this one, S sub n, is the sequence of partial sums. So S sub 1 and A sub 1 are the same. S sub 2 is the sum of the first 2 terms. S sub 3 is the sum of the first 3 terms. S sub 4 is the sum of the first 4 terms, etc. And what do you think the limit of S sub n is here? 5. So the limit of S sub n as n goes to infinity, in this case, you could write it as 4.9 bar, which is the same thing as 5. All right, any questions on either of those? So our goal right here is to be able to distinguish between A sub n and S sub n. So A sub n are the individual terms that we're going to add together. S sub n is the progression of adding one term at a time. So S sub 2, sum of the first 2. S sub 3, sum of the first 3. S sub 4, sum of the first 4. That's what we have to keep straight. The S sub n's and the A sub n's. Must keep them straight. All right. So this is the part, formulas for partial sums, that is very difficult, if not impossible. And what we are going to do is we are going to see that the only series that we're going to be able to find S sub n for are geometric and telescoping. And we'll talk about what these both mean later. But just as a heads up, that there's only going to be two types of series that we can find S sub n for. This one is a geometric sequence right there. That's a geometric sequence. What defines a geometric sequence is that you have a common multiplier. So a geometric sequence or series is it is the one example that it's just as easy to write it recursively as it is to write it functionally. This is going to be the most important series that we study, is the geometric series. And what is the common multiplier from one term to the next? Yeah, multiply by a half. So we just have repeated multiplication by 1/2. So they call this the R value, the common ratio. You could also write this in a functional way super easily. A sub n is equal to 1 over 2 to the n, if you used an n or whatever. Here it's written as an n. Here we have a k to sort of index through all the n values, so depending on how you want to think of it. But a sub n is going to be 1 over 2 to the n. Do you agree? So if we put our index values right down here, very easy to write a functional representation for the term. 1 over 2 to the 1 is a half. 1 over 2 squared is a fourth. 1 over 2 to the 3 is 1/8. Right, so the geometric series is a very nice series. You can write it recursively easily. You know, we just multiply by a half. You can write it as a function very easily, 1 over 2 to the n, if n is your index. Okay, so now the sequence of partial sums. Eventually, we are going to get to a place where we can, where we actually have a formula for the sequence of partial sums for a geometric. But let's try to discover what's happening here. So S sub 1 is a half. S sub 2, we add the first two terms. So we're going to add the half and the fourth and get 3/4. S sub 3, add the first three terms. S sub 4, add the first four terms. All right. So now they're saying, find S sub n. What is the pattern? Can we find a formula for S sub n? And the answer is yes, we can find a formula. S sub n is equal to, look at the denominator first, and tell me what the relationship is between the denominator and n. Two to the n, you all agree? Right? There's 2 to the 1, so 2 to the 1 is there, 2 to the 2 is there, 2 to the 3 is there, 2 to the 4 is there. And what's the numerator? 2 to the n minus 1. Right? It's just 1 less than the denominator. Now this isn't always the pattern for a geometric series, but this is the pattern for this one. There will always be a pattern for a geometric series, and again, it's one of the very few series that we can actually find in S sub n. So if we want to take the limit of this, the limit as n goes to infinity, well, that's indeterminate, right? 2 to the n minus 1 goes to infinity, 2 to the n goes to infinity, so right now it's indeterminate. And anytime we have a limit that's indeterminate, we have to do some manipulation. Here it's very easy to manipulate. What are we going to do? Split. Oh, we could. L'Hopital's is a way to go, for sure. We'd have to take the limit of a exponential with a base other than e, which we can do totally fine. Here it's just easier if we just split. If if we split, what's true about the 1 over 2 to the n? That's going to go to 0. Because in the denominator, we have something growing without bound. So the fractions are shrinking to 0. And the limit of 1 is 1. Limit of a constant is itself. All right. So that's it. So here is a formula for S sub n. And it's going to converge to 1. So the sequence of partial sums is converging to 1. So now we're kind of thinking of this kind of horizontal asymptote model. Right? The sequence of partial sums is converging. So the limit of S sub n is 1. So what we say then is that the sum of this series is 1. So this series right now is equal to 1. So whatever the sequence of partial sums approaches, whatever its limit is, that is the sum of the series. Just like over here, the sequence of partial sums here is 0.9 and then 0.99 and then 0.999. So this infinite series converges to 1. We have 2 infinite series that converge to 1. Do all infinite series converge to 1? Definitely not. That's bad. Yeah. 2 examples where they converge to 1. So that's interesting. That's not obvious. If you were to add these together, that it converges to 1? Not obvious. Okay. Now let's think, though, about this contrast. These terms go to 0, and we have convergence. These terms go to 0, and we have divergence. So when we look at these terms, you can say to yourself, oh yeah, these terms are going to 0 faster. Right? This denominator is an exponential. Right? We have 2 to the k. So this denominator is going to infinity faster than this denominator. This denominator is just n. Right? It's 1 over 1, 1 over 2, 1 over 3. So that is kind of like the 1 over x thing. Right? 1 over x didn't go to 0 fast enough. We had an infinite area beneath 1 over x, which is how we're going to kind of prove that this is infinite. But this one, if we're thinking about the graph, it's swooping down 1 over 2 to the k. The 2 to the k goes to infinity fast, so these fractions go to 0 fast. So very much like the improper integration. Let's see. All right, so that is the overview of sequences in series. Now we are going to dive in deeper to sequences, and then we'll get to series. So in your mind, when you're analyzing a series, you should be seeing 2 sequences. You should be seeing the sequence that does this for the sequence of partial sums, and you should see this for the sequence of terms, because the terms have to go to 0 if the sequence of partial sums is going to have a horizontal asymptote. So you've got to have those 2 sequences distinguished. This section will just look at the sequences. So when I see this sequence here, I'm sort of thinking, oh yeah, that's kind of like a sequence of partial sums. So if you're seeing this kind of thing that has a horizontal asymptote, then you should be associating that with the sequence of partial sums. All right, so here we have the definition again of a limit. And so here we're talking about the limit of a sequence. And notice that the red dots are the sequence values. Aren't they part of that black curve, which is a function, a continuous function? And so what this theorem is saying is that if the limit of the continuous function is L, then the limit of the sequence is also L. So if your sequence is embedded within a function that converges, then that sequence must converge also. So if this black curve converges to this L value of 1, then the red dots must also converge to the value of 1, whatever L is. Does that make sense? So if we've got a continuous function, any embedded sequence must also converge. And when we think sequence, remember, your domain for your sequence is a set of positive integers, or maybe it includes 0, depends on the sequence. But, right, so the distance between the inputs is always 1. We don't have a sequence where we're talking about a sequence where the index values are some weird fractions or something. The index values are always integers. So in other words, they're always spaced by 1. And so if we have a function that converges, continuous function that converges, then the sequence must also converge. The embedded sequence must also converge. Okay, so for this case, we have the sequence is a sub n is equal to n over n plus 1. If we were to take the limit as n goes to infinity, again, if you leave it like that, you see that it's indeterminate. The numerator is going to infinity and the denominator is going to infinity. And so what we want to do is rewrite it. So I'll just do this to indicate that it's infinity over infinity. I'll just put it above and below the equal sign. And so that means we need to do something. We have a subtlety here. So the L'Hopital's rule was mentioned, and that's a great avenue. But keep in mind that when we're talking about a sequence, we're talking about discrete values, so we don't have a continuous function. So usually, when we see an n, we're thinking dots, not smooth curve. And you can't take the derivative of a discontinuous function. But we just had this theorem that said, oh, if the sequence is embedded within a function, then the limit of the sequence is the limit of the function. So in practice, most of us are just going to, if we use L'Hopital's rule, most of us would just do this. We would say, oh, the derivative of n is 1, the derivative of n plus 1 is 1. And we would say that then the limit of that is 1. So that's what we do in practice. Technically, what we really are doing, though, just to be clear, let's write it down once, and that's totally fine to do it that way, even though n over n plus 1 is a discontinuous collection of dots. What we really are doing is applying this theorem where we're saying, oh, well, that sequence is embedded within this continuous function. So we're really using L'Hopital's rule on this continuous function here. That's really what we're doing to get the 1. But in practice, it's just kind of a tedious step to change all the n's to x's and then take the derivative. But just to make note that there is a subtlety there. That when you take a derivative, you can only take the derivative of a continuous function. And a sequence is not a continuous function. But if the sequence is embedded in a continuous function, you can take the derivative of the continuous function. Okay, so now something that's super important. The converse is not true. So converse will mean going the other direction. So let's see if we can understand converse. So this says, if the limit of the continuous function is L, then the limit of the sequence is also L. The converse would be, if the limit of the sequence is L, the limit of the function is also L. So the converse is false. So the statement is, limit continuous function is L, then limit of sequence is L. Converse, limit of sequence is L, then the limit of the function is L. That is false. Here's an example. So what we have here is this sequence, cosine of 2 pi n. So when n is 1, we have cosine of 2 pi, which is 1. This height is 1. When we have 2, we plug in 2 there, we get cosine of 4 pi. Cosine of 4 pi, also 1. Plug in 3, cosine of 6 pi. We've gone around 3 times. Cosine of that is also 1. So this sequence right there is the limit of a sub n, so as n goes to infinity, this sequence, all the sequence values are 1. So the limit of that sequence is 1. But if we graph the function, so the function f of x equals cosine of 2 pi x, there's the graph of the function. The blue curve is the graph of that function. That is an oscillating sinusoid, right? And what is the limit of this? The limit of the blue curve? dne, right? It's oscillating. It's not getting closer and closer. It's not getting arbitrarily close to some number. There's no horizontal asymptote. So this limit, all we can say is it does not exist. Okay, so continuous function converging means embedded sequence converges. But just because you have an embedded sequence that converges does not mean the function converges. And all of you, I think, can imagine a ton of different sequences in here that converge. You know, you could imagine grabbing that point and that point and that point and that point and that point. This sequence right there would have a limit of 0. That doesn't mean the function converges to 0, though. All right, so function converging means sequence converging, but sequence converging does not mean function converges. Everyone see the difference? Right here we have a continuous function that's converging to L. So if we drop an embedded sequence in there, it must also converge to L. Here we have a function that does not converge, but we can find a sequence that's within it that does converge. So continuous function converging means an embedded sequence converges, but just because an embedded sequence converges doesn't mean the continuous function converges. Most of the time we're going to be in that top case. But anytime we have a theorem, you always ask, is the converse true? Right? If A implies B, a natural question is, well, does B imply A also? Like, if I go this way, can I also go that way? Like, that's a natural question to ask anytime you have a theorem. Now, in math, if you can go both ways, usually they would say A if and only if B. They'll do an IFF thing, if and only if. And if they say A if and only if B, that means it doesn't matter. You can go A to B or B to A. So the notation that they would use is this. So this tells us that if A is true, then B is true, but also if B is true, then A is true. So the one that we are just looking at right now is this direction. So A implies B, but B does not imply A. So in our case right now, we're dealing with this. And the converse we just showed is false. B does not imply A. Right, limit laws. Very boring. They are what you would expect. They're just like the derivative laws or the integral laws. The limit of a sum is a sum of limits. So if you have two sequences that converge to A and B, if you add the sequences together, the limit will be the sum of the individual limits. In other words, the limit symbol, like the derivative or the integral symbol, can distribute across a plus or minus. You know, we've done that a lot, where we distributed our integral symbol. Same thing with the derivative, same thing with the limit. You can distribute it. Similarly with constants, if you multiply a sequence by a constant, you can factor the constant out. Just like a derivative, just like an integral. You have a leading constant, it can factor to the front. This one is different. It is not true that the derivative of A times B is the derivative of A times the derivative of B. I saw some of that on the test. That is not true. You cannot, and it's not true for integration either. For a derivative, if you have a product, you have to use the product rule. You can't just differentiate, multiply them together. Freshman dream. You can't do that with integration either. If you have the integral of a times b, you can't just, this is the one I saw a few times, you can't just integrate a, integrate b, and then multiply them together. Right? The integral of a product, we need to use integration by parts, we need to use trig substitution, we need to use powers of trig functions, pull off an odd, and do whatever you have to do. So this one is different. But for a sequence, two sequences that converge, you can take the limit of them individually. So this one is different. This one is very different. So let's highlight that one is different, and that one is different. So if you have a product of sequences, you can take the limits individually and then multiply the products together. If you have a quotient of sequences, you can take the limits individually and then divide them. Not a problem. Cannot do that with derivatives and integrals. Okay, so some terminology. We are going to say that the limit of a sequence is determined by the terms in the tail of the sequence. The front of the sequence does not matter. What matters is what's happening way out as n gets really, really large. You can have all sorts of wild oscillations in the first 1,000 terms. But if then it settles down, the limit of the sequence exists. Right? The leading terms of a sequence do not matter. So the leading terms or the front terms, however you term it, whatever terminology you want to use, the leading terms don't matter. I'll usually call them leading terms, and then the tail is what's happening out beyond when n is large. So the limit of a sequence, all we care about is what's happening way out there. So you can have two sequences that differ in their first 100 terms, but be identical beyond 100. They'll have the same limit. You can have this function. You can have that function. They can have the same limit. Only matters out in the tail. So the initial index of a sequence, for example, n equals 0 or 1, a lot of times it's not even specified because it doesn't matter. So many times for a sequence, we are just going to write this. We're not even necessarily going to say that it starts at 0 or it starts at 1. Because when you take the limit as n goes to infinity of a sub n, it doesn't matter what it starts at. You don't care about the first million terms. You care about what's going on beyond. So terminology. So we'll talk about the tail of a sequence, which means far out, and we'll talk about the leading terms of a sequence. Now, the leading terms are important if we're dealing with a series. If we're dealing with a series, and we just chop off these terms, then the remaining part of the series is not going to converge to the same thing. Right? If we're adding terms together, chopping off the leading terms changes the value of what the remaining terms will add up to. So for a sequence, it doesn't matter, but for a series, it does matter. In fact, for a series, the leading terms are more important because the trailing terms are getting closer and closer to 0, so they're not contributing as much. So here, the bigger contributions happen in front, but the series most of the time. All right, let's do some math. So in Calculus 1, you learned how to take limits. And the limits that you took in Calc 1 typically were limits of functions. The limits of sequences are no different. Sequences are functions. So let's dig in here. So we have the limit of n to the 12 over 3, n to the 12 plus 4. And right away, you see that, oh gosh, we have an indeterminate form. Right? We have infinity over infinity. We have this indeterminate form. So anytime we have an indeterminate form, we need to modify the look of whatever we're taking the limit of. Now, if this fraction were flipped, it would be easy. We'd split it. That would be the easiest way to do it. We can use L'Hopital's rule here. But how many times do we have to use L'Hopital's rule? 12 times. We have to be taking derivative, 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 derivative. That seems impractical. So what you should have seen in Calc 1 is that there are some algebraic strategies. One is to divide by the highest power of n or x, depending on what the variable is, that you see. Sometimes they say divide by the highest power of x or n in the denominator, but usually some sort of division is what is called for. So if we divide everything by n to the 12, we will have this. So we're going to divide the numerator by n to the 12. We're going to divide the denominator by n to the 12. So we're dividing all three terms by n to the 12. And these limits will be equivalent. That second limit, all we did was change the look. We didn't change the value. You know, multiplying by 1 is fine. We multiply by 1 all the time. If you're dividing top and bottom by n to the 12, you're really multiplying by 1. If you divide the top by 12, divide the bottom by 12, by n to the 12. So we're really just multiplying by 1. Everyone agree? N to the 12 over n to the 12. But instead of multiplying, we're going this way. We're saying, hey, let's do that and let's do that. We're dividing the numerator by that end of the 12, and we're dividing the denominator by that end of the 12. But we're really just multiplying by 1 again. OK, and this limit is what? 1/3. Because we see this little guy down here is going to 0. Because that has a constant numerator, an exploding denominator, which creates 0. Careful. Everyone follow? So that limit is 1/3. Now, if you want to do L'Hopital's rule 12 times, you'll get the same limit.
Well, couldn't you also, if you take L'Hopital's rule once, then that gets rid of the 4, and then you can like cancel?
Oh, that's a good point. Good point. Yeah. And that's a great point, that if we did L'Hopital's rule here, because that's a constant, we don't have this polynomial filled in with n to the 11 and n to the 10 and n to the 9. Yeah, good point. When we L'Hopital it once, that 4 will disappear, and we could cancel. Yeah, good point. Good point. If you can use L'Hopital's rule one time, sure, that's a great thing. This strategy is going to be more common for the things that we're going to see where you want to divide by a certain power based on whatever it looks like. But yeah, in that case, totally agree. OK, so how about this one? So again, you see that it's an indeterminate form. The numerator is going to infinity. The denominator is going to infinity. So you certainly could apply L'Hopital's rule. This one, it wouldn't be just once, but a couple times. You could apply it twice. But let's think about dividing by the, we have two choices. We could divide by n to the 5th, the highest power that we see overall, or we could divide by n to the 3rd, because that's the highest power in the denominator. If you divide by n to the 3rd, the nice thing about that is the denominator then becomes a constant, and you're not dividing by 0. If you divided everything by n to the 5th, then you'd have to deal with division by 0 in analyzing a limit where the denominator is going to 0. That tends to be a little bit harder than analyzing a denominator that's not going to 0. So usually the recommendation would be divide by the highest power in the denominator, so that, let me just write this out, so that you don't get that division by 0 thingy. So I'm dividing everything by n cubed. If you do n to the 5th divided by n cubed, you're left with n squared. Divide that one. Let's write one more step here. So this is going to be the limit of n squared plus 3 over n squared. And this is going to be 10 plus 1 over n squared. And we see for sure that these little fractions are all going to 0, or both going to 0. And so now we have the limit of n squared over 10 as n is going to infinity. And that limit is going to be infinity. So that limit does not exist, but we can be more precise. We can say that limit does not exist because the values are growing without bound. So dividing by the highest power in the denominator, usually that's the move. Okay, how about arctan? So the limit arctan of n as n goes to infinity. We all should know this one by now. We've seen it enough. What are we thinking that's going to be?
Pi over 2.
Pi over 2. Yep, we've done this one enough now. So the strategy then is going to be to treat these just like you treated functions of x in Calc 1. Hopefully you did enough of that none of this seems out of reach. Is there any questions on any of those two in particular? So in indeterminate form, you need to do some manipulation. Could be L'Hopital's rule, could be multiplied by division, manipulate it by dividing by something or whatever. Some sort of manipulation has to happen if you get an indeterminate form. So this one right here is indeterminate. Okay. Another important technique you learned in Calc 1, the log limit technique. These are other indeterminate forms that are a little more obscure. This indeterminate form is 1 to the infinity. If you look inside there, the limit of n over n plus 1, excuse me, n over n plus 5, the limit of that is 1. So this is indeterminate of the type 1 to the infinity. 1 to the infinity. That's an indeterminate form that hopefully in college algebra they talked a little bit about. Probably one of the most important limits of them all. You should have in college algebra learned about E. So we need to review E for a minute. If you have let me see. Let's do this first. Do you agree that the limit of let's just do this first. Do you agree that that limit is infinity? So if we take the number 1.1, we take a number that's just a skosh bigger than 1, and we let the exponent go to infinity. That's going to go to infinity. So again, we talked about that earlier. If you take a number bigger than 1, multiply it by itself, it grows. And you know that the limit as n goes to infinity of something a skosh less than 1, that's going to go to 0. So repeated multiplication of a proper fraction will go to 0. So then in college algebra, you should have been presented with this thing, 1 plus 1 over n to the n. The question is, what's the limit of that? And most of us would look at the base and say, oh, well, the base is always bigger than 1. 1 plus 1 over n, that's bigger than 1. For any n that you plug in there, that's bigger than 1. So most of us staring at that for the first time in our life would say, oh yeah, that's probably going to go to infinity. But what does it go to? What you should have learned in college algebra is that's where E comes in. The limit of that is E. 1 plus 1 over n to the n is going to converge to E. And in college algebra, they usually present it graphically. You know, you can graph 1 plus 1 over x to the x, and you see it's got a horizontal asymptote. But then in calculus 1, you should have shown that that's true using the log limit technique. Have you seen that? Log limit technique for showing that? Is that a real yes? So let's use the log limit technique here then. That's how you would show that. And notice that this is a 1 to the infinity indeterminate form. Right? The limit of just the base is 1, and the exponent's going to infinity. So 1 to the infinity is indeterminate. You can find examples of 1 to the infinity that go to constants. You can find 1 to the infinity that does go to infinity. You can find 1 to the infinity that goes to anything you can imagine. So that's why it's indeterminate. So 1 to the infinity is indeterminate. All right, so here's what we do. We first define a function that's equal to it. I usually will switch to x's just because I know I'm going to have to take a derivative. You don't have to switch to x's. But all these properties that we're about to use are for continuous functions. If you want to just keep the ends, that's fine. It's just a hard habit to break. So the log limit process, that exponent, we want to bring it down. So what do we do? Log it. Log it. Take the log of both sides, exactly. And when we take the log of the right-hand side, and when we say log, anytime you hear log in calculus, you should be thinking natural log. If it's not natural log, you will be told. When we say log limit, it's understood that when you hear the word log, it means natural log. Okay, so now we have that exponent out of the way. So now we take the limit of both sides. So the log limit process, you take the log, and then you take the limit. On the left-hand side of the equation, you are taking the limit of the natural log of y. Bless you. The natural log function is a continuous function. When you are taking the limit of a continuous function, the limit is stealth, and it can go to the inside. If you are taking the limit of a continuous function, the limit can move through continuous functions. It's very stealth. It can go right to the inside. Anytime you have a continuous function, the limit can move to the inside. And you do it all the time without even thinking. Like if you take the limit as n goes to infinity of, say, 1 plus 1 over n squared, what is that limit going to be? 1. Because the limit of this part is 0. 1 plus 0 is 1. 1 squared is 1. Right? That function is continuous, which means you can take the limit symbol and jam it inside. The squaring function is a continuous function, which means you can move the limit to the inside. So you do it all the time where you just move it in. You just haven't really thought about it maybe that's what you're doing. But you're moving the limit symbol through a continuous function to take the limit to the inside. You do it all the time with trig functions. If you're taking the limit of tangent of something, you would move the limit to the inside and take the limit to the inside and then apply the tangent. So you do it all the time. All right, so then over here, what we need to do is manipulate the right-hand side so that we do have an indeterminate form. So we want to manipulate the right side. What does this natural log business go to as x is going to infinity? 0. So x is going to infinity in both these cases. So here's an example, right? We're pushing the limit inside here. The inside goes to 1. Natural log of 1 is 0. But we never would rewrite this as natural log of limit of x over x plus 5. That's totally tedious. We just do it all the time. So if we were taking the limit of this, we just push it inside. That's the limit of 1. And that limit of 1, of course, is 0, or the log of 1 is 0. All right. And this guy right here, the x, that's going to infinity. Infinity times 0, we manipulate. It's indeterminate. And we manipulate it, and you do it the same way every single time. In order to create L'Hopital, we shove the x into the denominator as a 1 over x. Now you have an indeterminate form of 0 over 0. Right? The denominator now goes to 0. 1 over x goes to 0 as x goes to infinity. The numerator is going to 0. We already checked that. Now we can use L'Hopital's rule. So every time you have the indeterminate form infinity times 0, you just move it around so it becomes infinity over infinity or 0 over 0. It doesn't matter. This is the standard procedure, though. It's a little easier to push that into the denominator than to push the log into the denominator. So now you can use L'Hopital's rule. L'Hopital's rule says if we have an indeterminate form, we have two separate functions, so we have f over g. The quotient of functions is going to approach the same thing as the quotient of tangent lines. Quotient of functions is going to approach the same thing as the quotient of tangent lines. What's the tangent line? It's the derivatives. So in the numerator, the derivative of a log is 1 over the inside. Flip the inside. Times the derivative of the inside. Oh, it's a quotient. Yep, quotient rule. So quotient rule says low, that's the denominator, d high multiplied by the derivative of the, low d high multiplied by the derivative of the numerator, minus high, which is the numerator, times the derivative of the denominator, all divided by low squared. Quotient rule. The derivative of the denominator, 1 over x. What's its derivative? That's its integral. The derivative of x to the negative 1 is negative x to the negative 2. So negative 1 over x squared. I'm going to write that differently. Negative 1 over x squared. Let's stack it. Okay, now we have to simplify. Now we have to simplify. So, why is this problem even here? This takes too much space. So in the numerator, we have an x plus 5. Let's just do this carefully. So in here, x plus 5 times 1, that's just x plus 5. X times 1 is just x. So we have x plus 5 minus x. That's just 5. Over x plus 5 squared. And now we're dividing by a fraction, so we multiply by its reciprocal. Its reciprocal is x squared over 1. You don't need to put the over 1. So there, we're almost simplified. We have some common factors. We see that we could wipe out this x plus 5. That will take away that exponent, turn that exponent into a 1. We also see that we have an x right here. We could wipe that out, make that a 1. And it's going to make this exponent a 1. So when all is said and done right there, we're left with 5 and a negative x. So negative 5x divided by x plus 5. What is the limit of that thing? Negative 5. So at this stage, again, you have an indeterminate form technically, right? It's infinity over infinity. You could do the derivative thing. Also in college algebra, remember limits at infinity? If you have polynomials with the same power, top and bottom, the limit is the quotient of leading coefficients. You can also think of it that way. So however you think of it, you're going to end up with negative 5. All right, so now on the left side we have log limit of y. So we have natural log, we have limit of y. And our whole goal, we said that this thing is y. Our whole goal is to find the limit of y. So we're almost there. Where are we going to go from there? What do we do to both sides? Not multiply by
Or
e.
raise everything.
Yeah, so we call that exponentiating. Exponentiating. So that is the limit of the original function, the original sequence. That is our limit, e to the negative 5. So the sequence that we started with, that one right there, that sequence converges to e to the negative 5. That's what we just showed, using the log limit process. And that's exactly the same process you would use to show this. That 1 plus 1 over n to the n goes to e. These are not hard, but there are a lot of details. Quotient rule, dividing by fractions, L'Hopital's rule, there's a lot of stuff in there. No single step is hard, but there's like 6 steps all jammed together, so definitely practice those because there will definitely be one of these on the test. So what we did was created a function, took the log of both sides, took the limit of both sides, turned it into a L'Hopital. And then at the very end, exponentiate. That pattern is going to be persistent. Every single one of these. Function, log, L'Hopital, exponentiate. They're all the same. All right, let's go ahead and stop there. Enjoy the spring weather and all that daylight. Feels like spring for the first time, right? It feels a little springy out there. Wasn't it nice? I was trapped in this concrete cage all day. Today I will leave before dark. That is my goal.
You just jinxed it.
I'm going to walk back to my office. There's going to be like a pile of
Something. Pile of something.
Pile of something. Good thing is I better turn this off.